Hi everybody, and welcome to 7060 Module 5, Quantum Computing. This is a topic that I found very interesting. I've been exposed to quantum computing for 30 years, but never did any work in actually how it works and what the components were. So when I found out this was part of the class, I started to learn about it. My PhD is in industrial engineering, and I thought that was enough math, but apparently not. So I wanted to just give you, there's just a couple of slides, and I'm not going to talk for a long time because I think the lectures, the videos that I chose were great in giving you a lot of detail, a lot of information, but also some really practical applications that are coming in the future. So let's just get started. Okay, I thought the Google guys did a really great job in applying quantum mechanics to real life and things that, I just take for granted. So how plants make food from sunlight. This is just something that happens in nature, and it's super complicated, and obviously, apparently, according to Google, involves quantum mechanics. How light interacts with matter. So these are things that are in our world that we experience every day, that are part of the field of quantum mechanics, but that we just don't necessarily think about. And maybe one of you is a quantum physicist, so you obviously are an exception, but most of you, because this is a business class, might not be super familiar with this. How birds use the Earth's magnetic field to migrate. So I thought that was a really great example. This is something that I've always wondered to myself, like, how on earth do they know which way to go? How do they stay together? How do they know where to stop? And, just the ability to use, what is there in the Earth, that's super complex, but that it's just a part of their life, as an instinct. And then, of course, how qubits correlate their state with other qubits, aka quantum entanglement. So entanglement was one I liked a lot because I thought it was so neat the way I think Dr. Ghoshi explained it, where they connect in a way that isn't physical, and they know so much about the other qubit that when another qubit connects, it actually understands the state of the qubit it's connected to, and all the qubits that qubit had connected to. So you kind of think about this at sort of a very high level, because my brain doesn't work that way. It only works at a high level. And you think to yourself, well, that really is a much more complex, very theoretical way of these molecules and atoms connecting in this, quantum computer. So it made me feel a little better that it's like, okay, so it happens every day. It's all around us. I don't necessarily understand how these things take place, but they take place. And what we've been able to do over the decades, because I think Dr. Ghoshi also mentioned that this has been around for 30 years, in its like theoreticalness, but in I think it was 1994, Peter Shor actually came up with an algorithm that provided us a use case, an ability to think about how quantum mechanics and quantum computing could actually solve problems for us. Because in technology, when you're talking about technology, there's like technology for technology's sake, right? It's just something cool that's out there. But if we're not able to do something productive with it, advance humanity in some way, what's the point of it? And quantum computing, quantum mechanics and such has sort of been in that state for a long time. There are very smart, very dedicated people who understand quantum mechanics and understand the potential of a computing system like this enough to start putting together a computer that we can start to apply these types of use cases, or just basically understand how it works. And that's really the first step in in getting to an actual application of an advanced system like a quantum computer. This, when the Google guys talked about quantum computing, one of the myths that they set aside, basically, myth number one: quantum computers are already better than supercomputers. And the answer is no. This is a very typical technology disruption space. I would expect that quantum computers will, over the next, I don't know, 10 years, will become much more commonplace. More people, more organizations will have them and be able to experiment on them. At the end of the Google presentation, they talked about getting the developers involved because they want a lot of ideas on how to use this quantum system, how we can apply this. And that doesn't come from an isolated small group of super brilliant people. We've learned this over time in the technology space, that the more open a technology is, the more ideas you'll get, the faster your development happens. And for those of you that aren't as old as I am, you don't remember mainframe computers. So mainframe computers were around, I actually think Eric in the presentation from Google mentioned I think it's an ENIAC computer, which came out in the 40s, but just did simple calculations. From that, we went to mainframe computers, which are kind of like, when they first came out, they're probably very similar to what we've got now with a quantum computer. Very few organizations can afford them, from the standpoint of just the money to have, to actually build one. But then in addition to the money, you have to have, an environment that is conducive to getting these computers to work, right? So one of the biggest issues they've talked about is heat. Google showed a picture of them building a quantum computer, and you see that same, kind of interior that you saw in the video with Dr. Ghoshi. That was the IBM computer that was built. And then you see them covering it to create this environment where you can keep this computer so cold that errors are minimized. So when you think about the difference between a quantum computer and a supercomputer, just the idea that you have to be prepared for errors is an issue. Quantum computers can do very little right now compared to our existing, classical computers. But way back in the early mainframe days, it was the same situation. Computers could do very little. You had to have a very specific language. As a matter of fact, the initial mainframes, you had to use punch cards. So you would punch holes in a card and feed it in. That was the only way that you could communicate with this computer. And they were kept in water-cooled environments. They had actual plumbing that ran through the computer to keep the computer from overheating. I don't know if they were prone to errors. It really was just that the thing would break down. So I don't know if it's the same thing with quantum computing, but this was a common occurrence. The computer rooms that house these gigantic mainframes were humongous, and they were very, very expensive to maintain. They had raised floors, and like I said, plumbing that went through. They had air conditioning, underneath the floors that came through to keep the room very cold, the computer very cold. And so this was a barrier to entry. So as companies were able to afford a computer and a staff of people who understood how to use it, they differentiated themselves potentially from their competitor. They were able to do things faster and better than their competition, and it made a difference. This is when technology was really something that could really differentiate one one company from the other. As we move forward in time, this was probably like in the 80s, maybe 70s, we came up with mini computers. These are smaller versions of the computer. They could do, at first they did less than a mainframe did, but they did something specific. that was less expensive than a mainframe. You didn't necessarily have to have it in an air conditioned room. Maybe you could have it in a regular department and it could do something specific for the department. And then we got down to, symmetric multiprocessing and blade computing, and you got down to really fast individual computers that could do amazing things. And now most of us walk around with a smartphone, which is, to give it an example, this has the equivalent, capability of, the first, supercomputing mainframes. It can do so much on this, very small state. And they've said, you're never going to have a quantum computer on your laptop. And that might be true because, just from a physics perspective, you may never be able to keep, this type of technology cold enough. But that's the same thing they said about mainframes. People were never going to have their own computer. And when Steve Jobs said, my goal is to have everyone have a computer on their desktop, and Bill Gates as well. Everybody was about, having a personal computer. It was a crazy idea. So you never know. But the main idea is we've got to develop use cases. We have to, we have to find a way to bring people together so that they can figure out how applications can work on these computers, figure out use cases, and make it so that these quantum computers are serving humanity in a productive way. I kind of thought to myself, one of the advantages is that, it's going to be difficult for criminal organizations to get the resources to use this against us. And what, Dr. Ghoshi was saying was quantum computing in the security space was going to provide a key that was unbreakable, because they would have to defy the laws of physics in order to do it. So that was a great example of how this type of technology is really going to be able to advance us in areas of like security. So this is a very typical disruptive technology. It has all the, all the characteristics of like the old-fashioned mainframe, and it'll be really interesting to see how it advances, through the future. Let's see, next. I apologize for the way this slide looks. I actually took it directly off of what Dr. Ghoshi was talking about. And this is another, very typical technology slide where we see that this is the full stack set of vendors. So you've got, the big guys here, Google and Microsoft and IBM. Bell Labs was, I was surprised to see Bell Labs here. This was one of the original, supercomputing vendors. I didn't even know they were still around. So these are the old-fashioned, group that, except for Google, where they have the history and they really understand how technology has progressed and have been, investing in this space for many years, especially IBM. I remember them talking about quantum computing when I was there in the, mid 80s. So, and one of the important things about this technology that they talked about was that quantum computers themselves, just the hardware is, useless to us. It's just spinning around in this very cold space, and people are trying to figure out what to do with it or how it works, really. And that's what all those definitions were about, understanding how these elements of quantum mechanics come together in a computing space. Enabling technologies, now we're talking about like operating systems and things like that will help us to get this computer to do something predictable and replicable, so that we can start to understand how applications are going to work in this space. And then we get to this third area, software and consultants, where these people are going to be able to provide applications on top of an operating system, on top of the hardware, in order to create an environment where people are going to be able to do something useful with this quantum computer. And then finally, I really liked the discussion of the use cases, security that we've already talked about with Dr. Goshi, which it just provides a completely different level of computing that isn't something that we do at all now. I loved her example of the difference between a candle and a light bulb, right? So you get one candle or 100 candles, you still don't have a light bulb. It's a completely different technology, a different way of thinking, different use cases, and the ability to scale. So what that's kind of why she was trying to get across to us that our traditional way of thinking in classical computers is kind of irrelevant in quantum computing. It's just a completely different type of technology, works completely differently. And we have to, like in my case, I just kind of let go of the ability to control and understand it at a level where I get the way that, the way that data is moving through the computer. I just kind of let go because it's too much for me to think about. They mention a lot of times this idea of brute force, and when I was getting my PhD, it was in the engineering college, and I did not have a bachelor's degree in engineering, and a bachelor's degree kind of is where the engineers, they weed out people like me. You have to be able to do this sophisticated math in your head. You don't get calculators and things like that. And my advisor kept saying to me, okay, I want you to think of this a little more like higher level. I want it to be like graceful and smooth in your brain. All you're doing is brute force, which is going down different paths, trying everything out, making sure, like, is this the answer? Is this the answer? Is this the answer? And he said, I want you to think about it a little bit higher level, but I couldn't. Like, my brain doesn't work that way. So, and there are limitations to the way our brains can calculate things. Even in the, quantum physics, quantum physicists, their brain works a lot better than mine, but there are limits to the way that our brain can function. And when you get to even sophisticated supercomputers, they're doing things that we simply can't do in our brain. So it is important to understand that we're getting to a much more sophisticated level of computing for these, high computing tasks. So like security, right? So being able to connect companies together in a secure way so that data and information can pass without any fear of being interfered with. Drug treatment and development. This is something I'm very close to. My husband has stage 4 cancer, and we're going through a really very sophisticated treatment plan where we go from very traditional drugs to immunotherapy that is very specific to the genomic sequence of the tumor. And they have to use this data. It has to be updated on a regular basis so that they can apply the minute characteristics of these tumors to immunotherapy that's out there. And right now, it's very brute force. So, they say, okay, you're pretty close to this characteristic, which is something that this drug will work with. And we're going to try it out. These drugs are not like taking an aspirin, right? You have all kinds of complications and side effects and things like that. So you're putting the patient through a lot of discomfort, in some cases agony, just to try something out, only to have it not work. So, when you look at using a quantum computer that can apply all of the different elements of a genomic sequence of a tumor and be able to say, okay, so typically it works with this characteristic, but it doesn't work with these 3. So because we've got these 3 and not this one's not going to work. But being able to look at it at a level where combining all of the different treatments and looking at all of the different genomic sequences, it's going to be able to figure things out so much faster and so much more effectively. And the way that I look at it is we're going to be able to use drugs that maybe were never even developed for this use much quicker, applying it much quicker. So an example of this, there's an immunotherapy called Keytruda. You've probably heard of on advertised on TV. It was originally developed. Let me see if I can get this right. It was either originally developed for breast cancer or it was originally developed for skin cancer. And what they found through use cases was that it could be applied to the other cancer and work just as effectively, because it was more about the genomics than it was about the type of cancer. And they're using this more and more effectively. They're more confident in their ability to use it, but you're still talking about brute force, right? We're going to try it here, we're going to try it there. It worked on this guy but not that guy, this girl not this girl. And quantum computing is going to be able to look at this data in a different way and apply the knowledge that we have in a much more sophisticated way, just the way my advisor wanted me to look at math. So great hope for drug development and treatment development, especially in some of these more rare cases. Fusion energy, which I know absolutely nothing about, fertilizer production, because I have some background in gardening and I'm part of the extension office in both Florida and Michigan. I know that this is, again, another sophisticated area where fertilizers are, they really have to be applied in very specific situations, right? So you can't just apply one fertilizer to all plants or to all climates or to all soil types. You have to understand all of these elements first before you figure out whether or not this fertilizer is going to work in your fields. And this is really more about how do we feed the world more effectively. So do we have fertilizers that we can develop and produce that we can then use in these different climates where plants don't grow well, so like sub-Saharan Africa and things like that? Can we provide these types of innovations to improve the state of the world? So they're looking at these types of things as use cases eventually for a quantum computer, because obviously today it doesn't really work at all. It's doing very little, and they're just trying to figure out how to put things through without errors, right? So understanding like at what temperature or what's going on with this computer where it's actually producing errors versus something that's that effectively we can use. And then quantum machine learning, AI. So this is an obvious area where it can help, where you really have to go through just loads and loads of data and loads of different types of scenarios, like automated driving, where you really have to consider so much information in order for the car to make the right decision. So this is a natural place where things like quantum computing can make a big difference. So I learned a lot from this module, and I hope you did too. And that's it. Have a great day.